Anyway, I'm going to be giving a fairly general talk about, after we've heard the rather detailed material science in the previous one, about electrochemical techniques for application to anti-corrosive organic coatings. This presentation isn't quite original insofar as I gave a very similar talk a couple of years ago at the Oil and Colour Chemists Association, 100th anniversary in Leeds. But I'm hoping this audience is different. I don't think anybody here was there. So I've not really done any recent research in this area, and so the illustrative experimental work I've included here is actually 3 or 4 years old. But before getting on to that, I thought I'd give a little bit of background to my activities, or history, if you like, of activity in this field. So I actually started off working on paints nearly 50 years ago, and my thesis was on this, and I was always very interested in trying to get some sort of measurement out of the corrosion protection ability of a coating. It was a long time previously that in Jack's lab that anybody had actually looked at this, and this was Kit Maitland, and he'd actually put a coating on a metal and measured it. Jack himself felt it was a bit complicated system to try to understand, so he did all his work up to the point when I arrived with putting the paint not being on the metal, looking at the detached coating, because he was convinced that was the key to it all, assuming reasonable preparation of a substrate. So in that work, the detached resistance behavior was very, very extensively studied. And somebody yesterday was talking to me about D&I areas, these areas in the coating. And I gather possibly Stuart has got somebody lined up doing a bit of work on this. And this is still an interesting area, which Sina Jamali did some work relatively recently, certainly a long time since the original work. And I can't go into that in detail now because we've got other things to talk about, but you can read that slide there. There's a bit about where I published my work, and in the early days it was all in the Oil and Colour Chemists Association journal, which is, and more recently it's generally been in Progress in Organic Coatings. Now I'm going to talk about actually applying these methods to real systems, and I thought we'd just put this slide in here to show what's going on. So it's not typical insofar as this is a different sort of system, but we'll see more about that later on. So what have we got in the way of electrochemical methods? Well, it was way back in 1948 that Bacon, Smith and Rugg looked at 300 coating systems in seawater and came up with this criteria. And the 10 to the 8, 10 to the 6, and less than 10 to 6 as being good, fair and poor. And what we saw yesterday, I think it was Beatrice Bingo's paper, started looking at the 0.1 Hertz value. And basically that's probably the same, this isn't using EIS, basically that's the same as using, looking at DC value of the thing. And you've got this other measurement you can make of RN, which you get from the electrochemical noise data, which is again pretty much equivalent. So you can do this Bacon, Smith and Rugg method, got a Keith electrometer, that does effectively the same thing. It's not quite the same, but it can be used, and we are going to show some results from that. Electrochemical impedance spectroscopy, we've heard a bit about that as Beatrice used yesterday, or told us about yesterday, and it's popular. But really, when it comes to it, you want just 1 or 2 measurements from it, like the resistance or the capacitance. And EIS very good. We saw something yesterday about the scribes and disbonding. You get information about what's going on there. And there have been other techniques as well, which have been developed, and that would include the DC current interrupter technique. That Sykes and Tanabin, there's even been a standard produced on this. Pretty useful method, but not generally been taken up, I don't think. And then we've got the electrochemical noise method, which you heard Leo talking about yesterday. But of course, this is we're interested here in we're trying to apply it to coatings, and so I'll be talking a bit more about that in a minute. And I haven't got time really to go through the other methods, but we know about them for investigating corrosion with coatings, SVET and SRET. Nice to see Bob here. I worked with him a few years ago on that scanning, turning round and round anyway, wasn't it? And the scanning Kelvin probe is looking quite promising. So again, I've tended to be moving into interest in trying to get to a method that can be used in situ out on site. And that was done 20 or 30 years ago by Rowlands and Thompson, and the Gdansk group have done this with EIS. But the technique's getting more popular now because of the standard that's been produced on EIS. As we mentioned, the DC transit method, that's largely aimed at being used out on site. And what we're going to talk about today in more detail, and so some application of it, is the electrochemical noise method. So this was first used in 1987. When I first came across it was at one of these meetings at ACPOC. I've been lucky enough to attend all 7 of these ACPOC meetings. First one, was back in '89, and Skerry showed some work where he was assessing coatings with this method. So there's a few facts about the method. It's relatively simple, relatively fast, and is not intrusive. So partly because of that, going to that hearing that initial work, I got interested in it and worked in North Dakota State University with Gordon Bierwagen. I think came to the 1994 meeting, and we did this work on quite a number of different Navy coatings. It was early days of the technique, and it's certainly been developed quite a bit since then. And one thing about it is, in the original format, as designed by Skerry and so on, and others, it cannot easily be taken out on the site because you need 2 identical specimens, and that isn't great when you're trying to measure on a bridge or something like that, or even the hull of a ship. So it's some different way of arranging. The method was developed in the late 90s, early 2000s, and then there was a further development in the arrangement of the electrochemical noise, which was enabling you to make no connection at all to the substrate. That's still sort of being investigated. So what do you need for the standard methods? Well, 2 working electrodes and a reference. I suspect most people have come across to some extent in the past. There's data gathered over about 4 minutes at 0.5 second intervals. So you can continue to do this, and the work back in Bierwagen's lab was done, measurements were continuous. So you could see almost continuous anyway, once an hour for 2 days or 5 days or whatever. If you're talking about using it for, say, salt spray testing, you can take it out every so often and salt spray test and test it. So, yeah, again, this is how it works. People like Bob, who's here today, know more about all this than I do, but it's the application side that I'm interested in. So that's a typical plot. I think Leo put one up yesterday, the sort of thing you might get, and then detrend it. I think that particular example is showing how you can detrend data and get a better plot. And that's the key thing you're interested in, the resistance noise to the standard deviation of potential divided by the standard deviation of current. So that's the traditional way of doing it. It's Skerry talked about that originally, and in fact was used in the Bierwagen work. And this is the new-ish, well, not that new, but the arrangement that enables you to do it just on one substrate, and sort of by just jigging things around a bit. And of course, what we had to do was to show this was equivalent to the bridge, which it proved to be. And then we have this arrangement with no connection to the substrate, which is obviously good if you try not to make any, sort of having to make some cutting out the coating to make a connection onto the metal is obviously unattractive. So that was an advantage of this arrangement, which looks a bit like that. And again, work we did showed that this was getting similar results to what you would have got if it had been bridge. But you do have a problem here that with 3 different areas, you can't be absolutely sure which ones you're measuring, but there has been some clever work done, which by one of my students who sort of, by shifting the connections round and observing the values, you can work out something about what the 3 individual values are. So if you're going out on site, you certainly wouldn't want to be using the single substrate arrangement. You want to use, you wouldn't want to be using the bridge arrangement. You'd want to use something like single substrate or NOx. Just going to have a short drink. So just things you need to consider. You've got to have obviously a battery operated, or normally anyway, a battery operated device. You want minimal measurement time. And when you make the measurement, you want to be confident that equilibrium has been reached. And of course, you need a way of connecting to the external surface of the substrate. And that brings into the probes business. And that's quite an important part of using it outside, getting a suitable probe or electrode to connect to the surface. And this is a very basic sort of picture of what that involves. In the latest design, we don't have copper sulfate because that proved to be a bit too noisy, or just copper sodium chloride, but we now use silver chloride. And you can do different environments in there. Some of the work we've done suggests that you can use quite dilute chloride and still get a reasonable measurement. And you also need to be concerned about the time it takes for the coating to equilibrate. So we did a bit of simple work in the lab testing what happened to the resistance. Those are actually DC resistance values, and you see them sort of coming down and flattening off exponentially. And so you need to make some sort of suggestion as to how long you need to leave the pad or the probe on there. And we haven't quite got on to that one. And so typically 30 minutes would probably be enough. Right, so we did some work which I thought I'd include here, which is about using the electrochemical techniques, a couple of examples. And the first one, well, it's actually the same sort of coating, it's just the application is done in a different way. One is a sense of trying to sort out which the best coating is with lab tests, and that's what this part's about. And then the second part is sort of actually using the technique in situ. Now, this first part is using DC resistance, which is acceptable in lab tests, short-term lab tests, like we were doing a couple of measurements of a volt applied for a few seconds. But then out you don't want to necessarily apply a big voltage out in a real item in a real situation. So we use electrochemical noise in the second part. So what this did was just took some coating systems which are typically used for protecting metal archaeological objects. These were 4 coatings that were used in the museum in Gdansk, and these particular coatings had been used, but nobody really knew how thick they were going on, or which was the best. So they were interested in finding that out. So we did some simple lab tests using sort of the normal sort of things that we might find in the lab, spraying or brushing, dipping. I think we did dipping and spreading here for these particular experiments. And we measured the thicknesses, which we're able to do in the lab, pretty thin. You can see only a few 5 micrometers, 10 micrometers, so you're talking very thin coatings. But that's what you want with this sort of work, because you don't want the coating to be visible. It's protecting the object in the museum or outside, but not visibly. And so we did these tests with just simple drop tests to get some idea of the resistance and the corrosion protection afforded. And we then managed to apply those drops to the samples, both copper and steel, and some coatings were doing better than others, and some were the two-coat systems, as you might expect, were doing better than a single coat, and they were getting some rusting. So we were trying to relate that to our DC measurements, and that they did pretty well. The relation was good, in that, as we might expect, the lower values of resistance, as I said, is a DC, were related to the ones that corroded significantly, and the ones that didn't corrode at all in a relatively short-term test had much higher resistances. So we were able to give the museum an indication of which were the better ones. This picture is a little complex. This table rather, and relates really to the fact that it does depend on the environment and the type of coating and the application, what your criteria might be. So for this particular example, you might be saying that it's good enough if it's better than 1E6. Not looking at total immersion in seawater, the criteria for good and poor and middling will be slightly different. So the one that came out best was the Paralite 44. So that bit of work showed the DC resistance measurement as a lab method was working well, and helped the museum decide on the best coating. So staying with the museum, we decided to look at when it became available, to look at the using the thing on site, or in situ, as it were, some specific items that were in the museum, which we'll see in a minute. So we're using the procometer, which was talked about yesterday, and silver chloride are used in this work, not copper ones. And they were using 0.5% sodium chloride. And there's 3 of the items that were investigated. The second one looks a bit like wood, but it was actually metal. And the Otago ship, the brass bowls, and the bell was also a sword. In fact, you see the sword in this picture. So these are the measurements being made in situ with the probes attached, getting some idea of the state of the coating. And this bit of work was quite successful. That's not the greatest of plots, but it does show the sort of things that were done. You need to do the trending on the data set. And then we got all these values of resistance from the various items, and essentially the values varied, not big. There's quite a few small values, but we could see that the sword was pretty low. We knew it had a fairly low protection on it, and certainly wouldn't, probably a bit too low. They would be recommended to put a second coat on there. The Otago was fine, high enough, good quality coating on there. The bell and the bowls were somewhere in between. And we did do a little bit of work which showed there was some connection between the RN value and the coating thickness, but that's not been included in here. So, coming to the end of the talk now. So the electrochemical techniques to assess organic coatings have certainly moved on since the original BS Bacon, Smith and Rugg. And what my conclusion would be is that for assessing coatings in a lab, I'm monitoring samples in, say, DC, in salt spray tests. I put faith in DC resistance, so as well as the IS, probably could do noise, but it does suffer the whole problem of some not being totally, the reproducibility is middling, not great. So for field monitoring, I would advocate ENM, because that seems to be working quite well. And we need to do a bit more work in terms of sort of validating the NOx method, which obviously is an attractive way of going on this. And the plan would be, hopefully by the next ACBOC, to give industry reliable guidance it needs in this area. And so I'd like to thank the various people who worked on this with me, and of course the students who worked with me. That's not all of them, but a few of them. And in this particular talk, there's been work from the help from the National Maritime Museum, and Leather Sellers Centre was where that work on the individual, on testing the coatings in the lab was done. And I think that's probably the end of my talk.
Thank you, Douglas. Do we have any questions? Can I make one comment? I would be rather more nervous than Douglas seems to be about using electrochemical noise in field applications. There is a very marked difficulty in making good measurements when you have interference about, mains frequency interference and other sorts of interference. And I think you need to be very careful to validate your equipment and your measurement system if you're going to try and do that.
Yes, they do have a calibration box which we test it, but yeah, what's my response to that? In general, we haven't found it a problem, but we haven't done any particularly difficult sort of.
No, I mean you're essentially working in lab conditions.
Yes, you're right.
And whatever it might be. I think if you go to a real chemical process plant, for example, you've got much bigger problems.
Yes, and you've got to filter out or recognise when you've got extraneous noise in there, and just.
So, any other questions, Stuart?
Hello, yes, thanks, Douglas. Just going back to your D&I areas.
Oh, yes.
Do you think
happy with those?
Do you think they were an artifact of the polymers and binders that were present and available at that time, or do you think that they are generic across all polymer and binder types?
I think it's something innate in the coating material, like sort of big molecules that haven't quite sort of that are dead in the resin that sit there, and if you can get rid of those, like sort of by centrifuging or something and getting out all the big dead ones, then you have an improved system which will not show the same number of D areas.
So if I was going to ask you, imagine you could go back in time with your electrochemical noise gadget, would you be able to measure D&I areas more reliably with that apparatus?
You could use the ENM to measure D&I areas, no problem, but I would probably do it with DC because it's a bit easier.
You should look at Mike Tan's work if you're going to do that, and look at multi-electrode arrays, because that would be much more sensitive in terms of picking out individual areas.
Yes, I think that's
always the problem, isn't it? Well, you've got a 1 centimetre square area, but it may be a very small part of it, or a huge area. That's obviously going to be a problem, yeah.
Okay.
Yeah, thanks.
Thank you.
Hi, Douglas. Quick question. Could you comment on attaching your probes to the surface? I see most of the techniques you introduced are based on aqueous solutions. Is there a move towards a bit different systems? For example, gel electrolytes or something that's easier to use? Or how do you deal with that?
You need something to penetrate the coating and get to the metal surface. So aqueous solutions are going to be better. When we've tried using gels or that sort of thing, it just doesn't give a result. So it's going to be an aqueous solution of some sort, but you don't necessarily have to have anything that's very strongly chloride. You can get away with something with low chloride, 0.1% or something. We'll do it.
I'm just thinking about, for example, vertical surfaces. Like that you say they're not horizontal. It's nice to put your probe on.
You can attach your probe on
tongue somewhere else. And,
yes, you can put the probe on anything. Yeah, it's quite good.
Okay. Can't keep the water there, though.
Yeah.
Well, no, it'll diffuse in, we hope.
Okay, thanks.